Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show CFD flow simulation of an unmanned aerial vehicle or UAV using SolidWorks flow simulation. As it is having 4 numbers of rotors, so this is called quad rotor. You can see here the lot of parts are there. This is actually a motor radiator and this is the motor. Next one we have the propeller bed. This is the most important part of this analysis. So while starting this analysis, we have to neglect some of the unimportant parts to ease the simulation effect, and to carry out these calculations or iterations within a very short time, we have to neglect some unimportant parts, right? So in our analysis, most important part is the propeller. And in this analysis, what we'll do is we have to find out whether the quad rotor is capable of moving up or not. That means we have to see that buoyant force or up thrust, whether that will be capable of overcoming its weight, that to be seen. So in this analysis, we'll find out a lot of things like the pressure difference, which is actually responsible for the upward movement of this quad rotor. By the same time, we'll see velocity at different places, and also we'll select some kind of goals, that is the force exerted by these different propellers. And this force exerted by these different propellers are actually creating up thrust. And here in this case, we are providing rotation of these propellers in 2 different directions. One pair will be rotating in a clockwise direction and the other pair will be rotating with anti-clockwise direction. This is done to balance the counter effects of torque or rotational effects, right? And in our analysis, we have to define a lot of goals. Main will be surface goals, pressure, velocity, etc. at the different surfaces of these propeller blades. By the same time, we have to see equation goals, that means the pressure difference, and we have to find out upward thrust, and also we have to find out the net thrust, that means the upward thrust minus the weight of this quad rotor. If total thrust is more than the weight, then it will be capable of moving up. That's why in the equation goal, we have to find out the net thrust, that is the total thrust minus the weight of this quad rotor. Okay. So without wasting time, let us start our simulation. We are starting the simulation from flow simulation, and the environment of simulation will be initiated with the wizard itself. We are starting this simulation with the default name of the project as project 2. Next, it will be SI system, and pressure in this case we'll consider as Pascal, and temperature will be degree centigrade, and the angular velocity we'll consider as rotations per minute or revolutions per minute. Next, it will be an external analysis, and we have to exclude cavities with the flow conditions and also exclude internal spaces. Definitely gravity will be involved, as the buoyant force will be moving up and the gravity will be acting downwards. That means the weight of the quad rotor will be moving down and the upthrust will be moving up, and the difference of these two is actually creating the upward movement of this quad rotor. So gravity direction, you can see from here it will be y. Along y it will be minus 9.81 meter per second square, and along z it will be 0. And definitely rotation will be involved, and you are considering local regions averaging. Next, gases, we are considering air as the gas, and in this case we are considering humidity also, and we want to have humidity to be 60%. Next, default wall thermal conditions and roughness we are considering. Thermodynamic parameters, temperature will be 20 degrees centigrade, though it is not having that much of effect. We are setting this one as 20 degrees centigrade. And the velocity parameters, we consider that air will be moving along x direction. Let us consider the velocity of air equal to minus 10 meter per second, as we will be moving negative direction of x, and this air velocity is relating to rotating frame, and we are considering humidity to be 60% at a temperature of 20 degrees centigrade and pressure 1G1325 Pascal. Here in this case we are considering the upward movement of this quad rotor, so we'll consider the coordinate system to be y. Okay, let us finish this. Let us hide this part, and to ease the simulation effect we have to neglect some of the parts which is not important in this analysis. Let us do this one from component control. You can see we are having a lot of parts. From these different parts you have to eliminate some of the unimportant parts to ease the simulation effect. We'll neglect these parts one by one. We're neglecting this one. This is the bolt head, dummy rotor space here, that to be disabled. Propeller is very important, and bottom part, that means this one, that is important, that needs to be in this analysis. Propeller is very important, that is also required. This is actually propeller, that is also important. This is, let us say, this is also propeller, that is important. This one is the flange, that is not important. Let us say this one, this is bolt, not important. This is also unimportant. Bolt, unimportant. Let us disable the unimportant parts for this simulation. This is dummy rotor space. Propeller, this is required. Bolt, not required. Bolt. Top part, this is required. So which is not required, that to be eliminated in this simulation effect. Let us check the geometry. We have disabled the unimportant parts of this quadrature. Let us check the geometry and see whether it is okay or not. We're considering this one as an external analysis. Let us check this. Status is successful. Our model is ready for simulation. Let us see the volume at this moment. This is the computational domain. So everything is right. We can go for simulation right now. Right? This is our project 2. We have disabled a lot of components. The main parts in this simulation is the propellers and also this frame. Okay, so our setup is ready for simulation. Next, what we have to do is we have to provide that RPM of this different set of propellers, and in this propeller we have to create some kind of dummy spaces which is responsible for this rotation, right? And we have to provide those rotating regions. At this moment those are hidden, so inserting those rotating regions. Let us insert rotating region. We have kept those things hidden. We are planning to provide a rotation of 5000 revolutions per minute or RPM for a pair of rotors. Okay, let us provide this one as 5000 RPM, and we have to select that rotating dummy space. From the geometry itself we can select it. You can see these are the dummy spaces. First one is this one. 5000 RPM is equivalent to 83.33 Hz that we provided here. That will be rotating with anti-clockwise direction, counterclockwise direction, with angular velocity of 5000 RPM or 83.33 Hz. Done. Again we have to provide the same rotation for this propeller. So rotating regions, insert rotating region, and it will be again 5000 RPM, and we have to find out that dummy space. This will be number 3. Selected. Again this one also will be rotating anti-clockwise direction with an angular velocity of 5000 RPM or 83.33 Hz. selected, and the opposite two will be rotating with -5000 rotation per minute in a clockwise direction. Let us select that rotating regions again, insert rotating region, and that will be rotating with -5000 RPM. And this one will be rotor space 3. This one will be rotating with minus, that will be in the clockwise direction. Done. Now the last one is remaining, rotating region again, insert rotating region. Again that one will be rotating with -5000 RPM, which is corresponding to -83.33 hours. Done. So we have provided the dummy spaces for rotating regions instead of these propellers. Next to that, we have to provide some goals. In these goals, our main aim is to have upthrust and also the net force, which is equal to upthrust minus the weight of this quadrotor. We can see the mass of this quadrotor from tools and mass properties. We have already seen that mass of this quadrotor is 44 grams. To make it rounded, let us consider that mass of this quadrotor is 45 grams, right? So its weight will be 0.045 kg into 9.8 Newton. Okay. Now we have to select some goals. Let us select some goals from here. Insert some global goals. From the global goals, we want to see maximum and minimum pressure, and the difference of these two pressures is actually responsible for the upthrust. We can see total pressure, minimum pressure, and also the maximum pressure. First goal is selected. Let us select some goals again. Goals, insert surface goals for these different pairs of rotors, and the force will be in the y direction, and we want to find out upthrust or force in the y direction for different pairs of rotors. Let us select all the pairs one by one, upward direction and the downward direction also. One pair is done. Again, you have to select for this pair goals, insert surface goals. We want to find out the same thing, that means force in the y direction, that is upthrust. Let us select the surfaces for the propellers. Now we can select the downwards surfaces also. Selected. Next one, two more pairs are remaining. Again, goals, insert surface goals. We want to find out the same things, that means force in y direction. Let us select the surfaces. Downward planes also required. Selected. Now the last one. Again, goals, insert surface goal. We want to find out the same thing, that means force in the y direction. Let us select the surfaces. Green check. Done. All the surface goals decided. Now from these surface goals, you have to find out some kind of equation goals. first two will be actually working as this one and that one. These two are actually clockwise rotation. This is negative one. You can see this one and that one. 3 and 4, actually here it is this and that. That means surface goal force in y direction, this one will be actually negative, right? Okay. Now what to do is, for these 4 numbers of upthrust, we have to find out upthrust in the clockwise direction and upthrust in the anti-clockwise direction, right? So we have to select from these two, it will be upthrust in the clockwise direction. Okay. Goals. Insert equation goal. That equation goal will be obtained from pre-decided goals. The first two is actually negative direction, so we have to take the absolute values of these two. Let us select the absolute one. Absolute of first one plus absolute of the second one. Bracket closed. Done. So we can rename this one as upthrust in clockwise direction. Second equation goal will be upthrust in the anti-clockwise direction or counter-clockwise direction. Insert equation goal. And the goal will be obtained from the pre-decided goals. As this third and fourth one is positive, so we don't require to take the absolute values of these two. It will be surface goal of the third one plus surface goal of the fourth one. Done. And we can rename this one as upthrust in counterclockwise direction. Done. Next equation goal will be total upthrust. Insert equation goal. And it will be coming from the pre-decided goals. It will be the addition of clockwise upthrust plus counterclockwise upthrust. Done. And we can rename this one as total upthrust. Another equation goal is needed. Insert equation goal. It will be net upthrust. It will come from the previous goals. It will be total upthrust minus weight of this quad rotor minus, we know that weight of this quad rotor is 45 grams, so it will be 0.045 kg multiplied 9.81, bracket closed. So this is the net upthrust, that is total upthrust minus weight of that quad rotor. Green check. And we can rename this one as net upthrust. Finally, the last one, that means the pressure difference, is also needed, which one is obtained from the global goals. Again, insert equation goal. And that goal will be obtained from the pre-decided goals. It is the difference between maximum total pressure minus minimum total pressure minus minimum total pressure. Done. And we can rename this one as pressure difference. We have decided all the goals. Next one, we have to go for some kind of local meshing. Let us select that mesh. Insert local mesh. And for local meshing, we have to select that surfaces or local regions. Let us select the two regions. And refinement, in the cells we want 3 level of refinement. And here in this case, from advanced refinement we can move up to 3 level of refinement. And tolerance, you can move little bit of 1 plus. Let us see the display of refinement. Done. Let us select that global mesh also. Edit definition. Let us select the manual one. And we want to see the refinement level. It is refined up to 1 level. Go and check. Next one, we have to run this simulation. We can run it from here. Let's start a new calculation. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. The solver is finished. We can see the results from the solver window. That net thrust is 21.92 Newton, which is equal to upthrust minus the weight of that object. That means the object is capable of moving up. And also we can see the pressure difference is very high, which is responsible for driving the quadrator in the upward direction. Let us close this solver window and we'll see the results from the cut plots. By the same time, we'll see the dynamics of flow particles also. Let us close this. Now I want to see the results. First of all, we'll see the cut plots from top plane. We want to see pressure, velocity, etc. Let us see pressure from the top plane. To select the plane from here, let us select top plane and we want to see pressure. Green check. You can see pressure at the top of the blade is less. That means less pressure is there. Because of less pressure, it is moving up, it is moving high. And you can see in the down level, pressure is more. This pressure difference actually is responsible for the upward motion of this quad rotor. Let us see the velocity also. Velocity near the blade is high. You can see it is in the range of 547 meter per second approximately. And you can see different ranges are there. You can see in the form of animation. Let us see velocity distribution from the cut plots. Let us play. This is velocity distribution along top plane. Up the velocity is very less and near the blades the velocity of air is very high. Let us clear and hide this part. Next one we will see the pressure distribution. Let us close these things. Cut plot 1, clear and hide. And let us select pressure instead of velocity. Now we want to see the animation of this one. Let us play these things. You can see pressure at the top level is less, and as it is moving down, pressure is more. And because of this pressure difference, the quad rotor or quadcopter is moving up. Next to that, we want to see the surface plot. That means pressure distribution across the different faces of this quad rotor. Let us clear and hide this part. Next one, we want to see the surface plots. And from the surface plots, we want to see pressure distribution across different faces of this quadrotor. Use all faces and select. You can see the pressure distribution at different ranges, at different faces is different. Near the blade pressure is very less, and as it is moving down you can see the color is changing. By the color distribution you can see the pressure at the down level it is high, right? You can see here top part pressure is less, and down as it is moving here also you can see the pressure is more. Okay, let us clear and hide this part. Next to that we want to see the dynamics of flow particles, that means how the air particles will be circulating near these propellers. Okay, so flow trajectories, insert flow trajectories, and instead of 20 numbers you want to make it 200. Instead of pipes you want to make this one in the form of arrows only, and when you see pressure distribution near these propellers, let us select the surfaces. Grid check. So the particle study is running right now. This is the particle study. It is better to see the particle study in the form of animation. Flow trajectories. Let us play these things. Propellers are actually forcing these air particles downward to generate a upthrust, and finally this upthrust is overcoming its weight. More the upthrust, it is better for this quadrotor to move up. We can see these things in the form of some different sides. Let us view these dynamics of flow particles from front view and side view also. Flow trajectories. Let us stop this one, and you want to view these things in the form of animation from front side, right? In this way it will be better to understand the dynamics of flow particles. You can see how it is forcing the air particles from top to bottom and generating upthrust. You can see this from the side view also. From right pane we can view these things. Let us animate these things. You can see the dynamics of these flow particles. By the movement of these propellers, it is forcing the air particles downwards to generate upthrust, and because of this upthrust only, the quadrotor is capable of moving vertically up. Clear and hide these things. Next to that, we want to see the goal ports, which one we have already seen from the solver window. Goal ports, insert goal ports, and we want to see all the goals what we have decided before. All the goals selected. Let's see these things. These are the different goals which one we have already seen from the solver window. And better to see these things in the form of graphs. You can see it from summary and history. Our main concern is actually the total thrust and total pressure difference. We can see here clockwise thrust, that is negative thrust. The negative value actually is because of the rotation in the negative direction. Clockwise thrust, we can see two different rotors are there for clockwise thrust. In the first case, clockwise thrust is equal to 6.42 Newton, and second case it is 8.44 Newton. Sign is negative, that means it was moving in the clockwise direction. Next to that, we can see this is counterclockwise thrust. You can see after 384 numbers of iterations, counterclockwise thrust is 4.30 Newton, and for the second set it is 3.35 newtons. And from the equation goal, we got the final one. You can see total pressure difference is very high. We got the total pressure difference after 92 numbers of iterations. Its value is equal to 94 megapascal. Similarly, after 384 numbers of iterations, total clockwise thrust or negative thrust equal to 14.76 Newton, and counterclockwise thrust, that is positive thrust, you can see here it is 7.64 Newton. Now next one, we can have a total thrust. It is the addition of clockwise and counterclockwise thrust. Total thrust equal to 22.40 Newton, which is more than the weight of this quad rotor. And finally, you can see the net thrust. It is the total thrust minus weight of this quad rotor, which is equal to approximately 21 Newton, which is very high compared to the small weight of this object. From this analysis, we could find that the net thrust is positive, which means the quad rotor is capable of moving off. This is all about today's CFD analysis of an unmanned aerial vehicle. Instead of stopping it here, we can do something else, like we can go for some kind of parametric study by varying the sizes of these impellers, and also we can do something like by changing the different rotations of these impellers, we can have different set of net thrust. And finally, from these things, we can have an optimization of dimensions of this impeller, and even we can have an idea of minimum rotations of this impeller. Okay, so this is all about today's analysis. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.